All right, so we've derived the vertical effective stress equation, and there is a little bit of a complicating factor that I wanted to talk about here, and then we'll do an example problem, computing vertical total stress, pore pressure, and vertical effective stress using Excel. So first, the complication is that sometimes there is some finite contact area in between soil particles. So the particles touch each other, and the area can't be zero because if you have a force acting over zero area, the stress would be infinite and the soil would break if the stress was infinite. So when you push two soil particles together, soil particles, like a sand particle, is really hard. It's made of quartz typically, but it's not rigid. It does have some deformability. So when they push against each other, there's some deformation that happens, and then there's some contact area. That contact area does not have water pressure acting on it, right? It's just solid to solid contact, so the influence of water is not there. That has an impact on effective stress. And so to illustrate the concept, what I'm going to do is use this case of a ball resting in a cylinder. So we have this ball right here, and we've lowered it into a cylinder with cross-sectional area A, and we'll assume that the cross-sectional area of the ball is identical to the cross-sectional area of the cylinder. So A is the cylinder area, N is the resultant force acting on the bottom of the cylinder, and the ball is submerged, so that resultant force arises from the combined effects of the weight of the ball and the weight of all of the water that's inside the cylinder that's not inside the ball, right? So it's the rest of the space. Now, if we zoom in right here, take a look just at that little contact surface, what we get is something like this. This is a zoomed in side view of the contact between the ball and the bottom of the cylinder. And you do have this range right there. There's a little region, maybe I'll even draw it in a blue line, right? There's this little region where the ball is flat, and it gets flattened out and presses against the cylinder. So you get some finite contact area, and we're calling that contact area A sub C, right? So that's because the ball is a deformable material, and it will bend a little bit so that you get this contact area. And then of course you have water pressure acting in the space in between. It acts on the ball in a normal direction, and it acts on the bottom of the cylinder as well. Okay, and then there's a particle contact force, right? The ball is pushing down on the bottom of the cylinder, and that contact force is P prime. So we have all the variables defined. Oh, and then this is a plan view. So if you look from the top down, right, this is the cylinder, and the ball just barely fits inside of the cylinder. And then this little blue circle there is where the ball is resting on the bottom of the cylinder and is forming a contact with the cylinder. Otherwise, in the other annular space right there, the cylinder is in contact with water, not with the ball. So the cylinder cross-sectional area is A, and this one cross-sectional area is A sub C. Okay, now if we do vertical force equilibrium of these different forces that we have going on, okay, the normal force is equal to the interparticle contact force plus the water pressure integrated over just the part of the area that's in contact with water, right? So you have the solid to solid surface force is P prime, and then the other area, there's water pressure pushing down. So the vertical force resultant at the bottom is equal to P prime plus that water pressure at the bottom times A minus AC, where A is the total area, AC is the contact area. Then what we said before was that vertical effective stress is the average of the contact forces divided by the area. The reason why we've done a cylinder is that it's easy for us to know the representative area. It's just A. So if we divide by A, we get N divided by A, which is equal to the vertical total stress. Then P prime divided by A, which is the vertical effective stress, plus this pore pressure times 1 minus AC over A. And we'll introduce a new terminology. AC over A is equal to lowercase a. Both AC and A are constants, so we can group them together into another single constant, lowercase a. So what we end up with is a little bit of a modified equation for effective stress. And actually, I've inverted it here. I'm expressing vertical total stress as effective stress plus pore pressure. Before we did effective stress is equal to total stress minus pore pressure, so just a small change to the equation there. Okay, and then we have this 1 minus a term that gets added in. Now for most soils, we can basically assume that a is 0. So if a is equal to 0, then this term becomes 1, and you just get the original effective stress equation that we already derived in the previous lecture. And that's almost always what we assume for most soils. There are cases, though, where a might not really be 0. A good example is if you have soil particles that are cemented together with an impermeable cementing agent, something like calcium carbonate. That's a common mineral that gets deposited at interparticle contacts. Basically, calcium carbonate is dissolved in the water, and then it comes out of solution at the particle-to-particle contact and forms a mineral forms this mineral deposit that cements the particles together. And now the water pressure is not acting over that full cemented area. So old soils that have had a long time for these mineral deposits to form, may be a little bit cemented, may have a significant contact area. Certainly sedimentary rock, that has a big contact area. So sometimes for rocks, we do modify the effective stress equation and we introduce an A parameter in there. All right, now let's move on to doing a quick example problem. And I just want to walk you through how to solve a very simple example problem to compute vertical total stress, pore pressure, and vertical effective stress. So we have a layered system here with 3 different layers. Layer 1 has a total unit weight of 18 kilonewtons per meter cubed. Maybe I should add subscripts here. 1, 2, 3, right? 3 different layers. Layer 2 is 20 kilonewtons per meter cubed, and then layer 3 is 21 kilonewtons per meter cubed. And what we're going to be asked to do is calculate sigma v, u, and sigma v prime. Okay, and I think that we can sort of qualitatively already sketch these without putting numbers to them. Then I'll go to Excel and we'll get the numbers and we can come back over and look at this PDF file. So if we focus first on just vertical total stress, all we're doing is integrating the total unit weight with depth. So we know that the slope of this curve is going to be equal to unit weight. So we have a lower slope in the top layer, a little bigger slope in the bottom, and then the biggest in the middle, and then the biggest slope in the bottom. So qualitatively, we should have a line that goes like this, then has a bigger slope, and then has a bigger slope yet down there. And we'll call that one sigma v. Now for pore pressure, the water table here is at a depth of 1 meter, right? If we look here, that water surface is at 1 meter depth. So the pore pressure is going to be 0 until we get down to the water table. So the water line is going to start there, and then it's linear, and the slope of this line is going to be the unit weight of water, which is 9.81 kilonewtons per meter cubed. So roughly half the slope of the line segment there, right? That soil is twice as heavy as water. So anyway, we've now drawn what looks like our pore pressure. And this is a qualitative sketch again. I'm not putting any sort of numbers to this yet. We'll do that in just a minute. And then if we want to draw effective stress, it's equal to total stress minus pore pressure. And actually, I've left out part of the pore pressure. We should draw it as a vertical line right there along 0. So it's not that it's undefined above the water surface, it's that we're assuming it's 0, right? So now we can do the subtraction. So if we do that subtraction, we're going to come down to here, right? So the pore pressure is 0 in that range, so the effective stress is just equal to the total stress. Then it's going to change when we reach the water table, and we start getting a reduced slope there, and then like that, and then it'll come like this. So that'll be sigma v prime, right? So we expect it to be something like this. I don't know if I drew it all that well. Let me zoom in and draw it better. It looked like the slope became negative. Once we reach the water table here, right, now we start getting a change in slope. So there, I drew a positive slope. Then it still is going to increase when we get to the layer 2. And then across here so that I didn't do a very good job with lining these things up. Then it'll go like that. Let me adjust this green line so that it matches. Get down to the third layer, and then the slope changes. Now it doesn't go to sigma v prime. Here we go. All right, good enough. So anyway, that's what I would expect to find when we do these calculations. It's always important to know qualitatively what you're going to expect. Then you have kind of a sanity check when you do the number crunching. So let's go to Excel. And I've set up a set of columns here, which is what we're going to need to solve this problem. I'm going to put my keyboard here on my Microsoft Surface. Yes, exit tablet mode. Okay, so we have depth D, and then we have unit weight. You may be wondering how I got that symbol font in there, the Greek symbol. Well, I just wrote the Roman letter G and then changed the font to appear symbol font, and then you get Greek letters, which is kind of cool shorthand. Then we have kilonewtons per meter cubed. Again, the 3 is a superscript, so it's good practice to actually format your headings so that they have things like superscripts and Greek letters, right? It makes it look nicer. Then we'll have vertical total stress, pore pressure, vertical effective stress. So for the depths, what I'm going to do is just pick depths where we need them to be. I'm not going to put like 0.1 and go all the way to 6 because I want to paste this file into the PDF. So what we're going to do then is put one depth at 0, then we'll need a depth at 1 because that's where the water table is, right? Any spot where we have a change, we need to put a depth. Then we'll have a depth at 2 because that's the transition from layer 1 to layer 2. And then we'll have a depth at 4, and then maybe we'll draw it a little further down, so I'm going to put another depth at 6. So let's come back to Excel. We're going to have 0 for the top, then 1, 2, 4, and 6. And those are the minimum set of depths that I need to draw the correct profile. Okay, now the total unit weight was 18 kilonewtons per meter cubed in the top layer, 18. And then once we get to a layer interface, now I'm at 2 meters, right? I'm going to put the unit weight from layer 1 because the way that I'm going to do the integration, I need to use layer 1 in order to compute the stress at layer 2. So that's a little trick too. So I'm still going to put 18. Then when we get down to 4, the unit weight is going to be 20 because now we're going to be integrating over layer 2. Then when we get to 6, it's going to be 21 because we're integrating over layer 3. And the way that we're integrating will make sense here in just a second. Now for sigma V, I know that the vertical total stress is 0 at the ground surface, so I'm just going to put a 0 in there. Then what we're going to do is just integrate the total unit weight over depth. So I'm going to say equals C2 now, right? So it's the previous value of sigma V plus the unit weight times the difference in depth between the current point and the previous point. So times A3 minus A2. Push enter, and then we get 18. So it's pretty clear we've just integrated 18 over 1 meter. But now the equation's done. All I need to do is drag and drop, and I've got the vertical total stress for the entire profile. And now you can see down here, the reason why I put a 21 in this cell is because we're doing 21 times 6 minus 4, right? The reason I put an 18 in this cell is that this number is equal to the previous stress plus 18 times 2 minus 1. So we're integrating on the interval from 2 to 1. All right, now for pore pressure, I know that it's 0 at the surface, and then I know that it's 0 at a depth of 1 meter because that's where the water table starts. And now we can start putting in our equation. So as we get to a lower depth, we're going to have equals the unit weight of water, put in 9.81 times the difference in height between the current depth and the previous depth. And you could even code in gamma W up on top if you wanted to, and use the $ references to make sure that you're always reaching the same cell. But now we've got the whoops, I forgot to add the previous value. So when we're integrating, you always have to add the previous pore pressure. There we go. And now we can drag and drop. and you get the water pressure versus depth. I'm using 9.81 for the unit weight of water. Sometimes people use 10. That's okay too, but I'm going to use 9.81. 10 does make the calculations a lot cleaner, right? We're using like integer values of depth, and these would be really nice, clean numbers. Okay, then to compute sigma v prime is really easy, right? This is the equation I said you should memorize. It's just equal to sigma v minus u. So column C minus column D, we've got that cell in there, and then we drag and drop, and our table's done, right? And then if we wanted to make the plot, we could do insert, I think I'll do a scatter plot. I have to admit I'm not very good at doing Excel. So I'm going to do a scatter plot with straight lines. Select data, add, then we'll do y-axis is going to be depth. X-axis, let's put vertical total stress. And we'll do OK. And then let me come and fix one thing here. The axes. Alignment. Axis options. Okay, here we go. Reverse. So values in reverse order. Right? So instead of making the depth values negative, I've kept positive depth values, but I put them in reverse order. And now you get exactly the plot that you want. Okay, now let's come in here. How do I get back? Select data. We're going to add another series. I warned you, I'm really bad at Excel, so this may be a little bit slow and painful to watch. I'm sure all of you could do it much faster. Let's select now pore pressure. All right, so we've got I don't know why that window's so big. We've got total stress and pore pressure. Now we're going to add one more. Oh, I should label these so it shows up in the legend. Here we go, depth and sigma v prime. And I messed something up there, really proving my inability to do Excel here. So the x values are sigma v prime. Y values are, oops, I think I picked unit weight. Let's do depth instead. Okay. There we go. That looks right. Okay. And then maybe I'll edit this one to be pore pressure. By pore pressure, what we refer to is just the water pressure in the pore space of the soil. So it's in between the soil particles. Then this one is going to be total stress. Then if we really want to do this the right way, we need to add some labels. Axis option, here we go, labels. Number, tick marks, line fill. Well, this is frustrating. Horizontal value. How do you I'm struggling to find where to enter the name of this axis. All right, so I took a little break there to figure this out. I'm really not very good with Excel, as I said. So anyway, here I've added a label on the x-axis, which you have to do. If you forget to add labels to your axes, you'll be docked points in your homework. So this is vertical stress or pore pressure in units of kPa, and then depth in meters. And let's see, the way that I added it was to push this little plus, and then you can select the entities you want to include in your plot. So anyway, now we have this nice plot, total stress, pore pressure, effective stress. What I'll do is copy these things and paste them into the PDF so that they'll be in the notes when you download these. A little strange, it looks like there's something underneath there. Anyway, there's the table, and I hope I can paste the figure as well. Let's see if we can do that. Yes, it worked. All right. So we've got both of those things, and you have the video showing, how we got these. Now, whoops. Okay, now one more thing I wanted to talk about is the concept of buoyant unit weight. What we just illustrated is the method that I recommend for computing effective stress. First, you compute the total stress, then you compute the water pressure, pore pressure U, then you compute the effective stress as the difference between those two. If you always use that procedure, you will get it right. You will never go wrong using that procedure. Some people like to shortcut that though. They don't want to compute total stress and pore pressure first. They just want to go straight to effective stress. So there is a trick of using the buoyant unit weight for cases where you have a hydrostatic water table. So if you have horizontal water surface, there's no seepage happening, then the water pressure below the water table is just equal to gamma W times depth below the water table. And so there's a trick that you can do. If the water table is hydrostatic, you can use the buoyant unit weight here, which is defined as gamma prime. Gamma prime is buoyant unit weight, and it's equal to gamma minus gamma W. Okay, and all you're doing is basically shortcutting the calculation of effective stress by skipping the sigma V and U steps, lumping them together in one step. So basically, you use gamma above the water table, where total stress is equal to effective stress, and gamma prime below the water table, and you directly get sigma V prime. So let's go back over here. We know that we've got these values of sigma V prime, right? 0 at the top, 68.95 at the bottom. Let's go down to this other tab, and we've got our depths. Let's see, it was 0, 1, 2, 4, and 6. Gamma was 18 at 1 meter depth. Now I'm going to use gamma prime. So I'm going to do equals 18 minus 9.81. So 18 is the total unit weight, 9.81 is the unit weight of water. So now here is the buoyant unit weight at a depth of 2 meters, right? So that's below the water table. Then at 4 meters, it's 20 minus 9.81. And at 6 meters, it's 21 minus 9.81. And then we can just do sigma V prime is equal, well, it's 0 at the surface. And then we can integrate as we were doing before. It's the previous value of effective stress plus the unit weight, either buoyant or total, times the change in height over that interval. So we get 18. And you can see we still get 68.95 at the bottom. So we've got the exact same effective stress profile, but we've skipped the step of computing sigma V and U. So it's kind of a shortcut, right? You can see that these are exactly the same. I would recommend not using buoyant unit weight. And here's the reason why. If you run a computer program, let's say, and you put in your soil properties, you make this figure and it shows, say you're solving a slope stability problem, you can have the soil in there and then you assign unit weights, and you have to go to the city council and show your results or something like that. Okay, if you show that figure, you can say, well, I use buoyant unit weight below the water table and total unit weight above the water table. The client will have no idea what you're talking about. On the other hand, if you draw the soil profile, you put your unit weights, and then you draw a line and it's blue and it shows right where the water table is, that's much clearer to the client. You're saying, here's the soil, here's the water, and then we did our analysis. And if you do it that way, the computer is computing total unit weight, it's computing pore pressure, and it's taking the difference, right? So first of all, it's clearer, right? Instead of having 3 lines like this, you would end up only with this line, and it wouldn't be all that clear, right? So including the total and pore pressure, total stress and pore pressure is a good idea. Okay, the other problem is that we had this caveat in here that buoyant unit weight is a trick that only works if the water table is hydrostatic, right? You must have a hydrostatic water table in order for this trick to work. If you have any kind of seepage, then the water pressure below the water table is not equal to the depth times the unit weight of water. It's going to be something different, and the pore pressure is going to be different from what you would assume, and you would get the wrong effective stress. So it's clearer to just do it the old-fashioned way, and it avoids potential pitfalls of getting the wrong answer in some cases.